Today we are diving into a truly revolutionary piece of technology for searching through complex data. It's called ACORN, and it solves one of the hardest problems in modern data retrieval. And before I go any further, I just want to take a moment to acknowledge the people who made this possible. This work comes from a brilliant group of researchers: 𝗙𝗢𝗢𝗏, Carlos Guestrin, Peter Kraft, and 𝗏𝗏𝗏𝗀. So a sincere thank you to them for pushing the entire field forward. The best way to understand ACORN is to start with the search problem it's designed to fix, because this issue has been a massive pain point for developers everywhere. So let's start from the core issue. There's a tiny little word that causes a huge technical challenge: the word AND. Modern search systems, especially those powered by vector embeddings, are fantastic at understanding meaning. Think of an embedding as turning an image or a sentence into a string of numbers that represent its concept. Show the system a picture of a golden retriever, and it can instantly find thousands of conceptually similar images. That part is easy. Where things fall apart is when you want something that is conceptually similar and also meets a very specific rule. The research paper gives a clean example. Find an image that looks like a dog but has the metadata tag cat. This kind of task is incredibly common when trying to detect mislabeled data, and the moment you introduce that AND, things get complicated very quickly. This combination of similarity search plus rule-based filtering is called hybrid search, and it powers so many real-world experiences, from shopping to research to analytics. Think about searching for a shirt that looks like one you saw and is under $20 and is available in your size, or asking for scientific papers with a natural language question and only wanting results from the last 2 years. This is the kind of search everyone expects, but at scale, doing it accurately and instantly has always been a challenge. So why is hybrid search so hard? Most systems rely on either pre-filtering or post-filtering, and both approaches break down for different reasons. Pre-filtering sounds logical. Start by narrowing the dataset using the rule and then run the similarity search on that smaller pool. But if the filter is broad, you're still stuck searching through millions of items. It's slow. Post-filtering does the opposite. It finds the most similar items first, then checks whether they match the rule. But there's a hidden trap here, and it's a big one. If the items most similar to your query don't satisfy the filter, the system has to expand its search radius again and again. It's like zooming farther and farther out, desperately trying to find something that fits. This creates huge delays. The research paper calls this negative query correlation. The visual example explains it perfectly. The green dot is what you want, but all the items that satisfy the rule, the blue dots, are on the other side of the dataset. The system has no choice but to crawl across the entire space, making post-filtering nearly unusable at scale. Before understanding ACORN's breakthrough, you have to understand why pure similarity search is already so fast. The hero here is a method called HNSW, Hierarchical Navigable Small Worlds. The name sounds intimidating, but the idea is beautifully simple. Imagine your dataset is a massive city. HNSW builds a multi-layered map. The top layers are like express highways that get you to the right region quickly. Then you drop into the main streets, getting closer, and finally, you move through the small local roads to reach the closest point. This hierarchical structure is why HNSW is blazing fast for pure vector similarity search. But HNSW still struggles with the AND problem. It wasn't designed to handle filters gracefully, and this is where ACORN's real genius appears. Instead of discarding the HNSW map, ACORN enhances it with a superpower called predicate subgraph traversal. Imagine applying a filter, say you only want coffee shops. In ACORN's world, every building that isn't a coffee shop instantly becomes invisible. Roads that lead only to houses or parks disappear too, but all the coffee shops represented by the green dots remain connected through the paths that matter. You are left with a clean, fully navigable city made only of the places you care about. The magic happens during the index building process. A normal HNS-W graph connects each point to just a few neighbors. ACORN takes the opposite approach and intentionally overconnects everything. It builds a far denser graph with many more links than usual, creating a thick web of redundant paths. And that redundancy is intentional. It's the insurance policy. No matter which nodes disappear later because of your filter, there are enough backup paths left to maintain connectivity. A graph that seems overly dense at the start becomes the smartest possible structure once you apply filters. All of that is clever, but the results are what make ACORN feel like a complete breakthrough. The performance improvements are not small, they are dramatic. On large datasets with 25 million items, the paper shows that ACORN can be more than 1,000 times faster than older hybrid search methods, while keeping the same level of accuracy. The performance chart makes it obvious. Accuracy, or recall, is on the vertical axis, and speed queries per second is on the horizontal. The goal is to be in the top right corner. ACORN's line sits in a completely different league from everything else. At any accuracy level you choose, it is simply faster. So what does this mean outside the world of research papers? It means all the intuitive, complex kinds of search people naturally want are now possible at full scale, without the system slowing down. You can mix visual similarity with price filters on shopping platforms and get instant results. Researchers can combine conceptual ideas with precise metadata filters. Data scientists can find strange anomalies in giant data sets in seconds. ACORN unlocks an entire generation of intelligent applications that understand hybrid queries the way we think. By solving the AND problem so elegantly, ACORN removes a fundamental performance barrier that has been holding hybrid search back for years. It makes these advanced searches not just feasible, but incredibly fast.